Yep. Keep going.
Long before battery-powered metal detectors ever beeped on a hillside, and centuries before ground-penetrating radar could scan beneath the soil, prospectors were discovering massive mountain gold deposits using nothing more than their eyes, a basic understanding of geology, and an ability to read the chemical footprint left behind by the Earth. Electronic detectors are remarkable tools, but they suffer from a fundamental flaw. They only tell you what is sitting directly beneath your search coil, usually no deeper than a few inches to a couple of feet into the soil. If a multi-million-dollar gold deposit is sitting 50 feet inside a solid rock cliff, or buried beneath 20 feet of dense mountain overburden, a metal detector will remain completely silent. You could walk directly over the world's next great gold vein, sweep your coil across the surface, and hear nothing at all. To find true, undisturbed mountain gold, you cannot rely on signals from a machine. You have to learn how to read geochemical clues. When deep geothermal forces push gold-bearing liquids toward the surface, they do not just deposit precious metal in a neat, isolated line. They scorch, alter, dissolve, and re-engineer hundreds of thousands of tons of surrounding rock. They leave behind massive chemical halos, broad, sweeping signatures written into the landscape through altered minerals, strange soil color changes, structural fractures, and indicator plants. These clues act as a giant visual roadmap, directing you straight to the heart of the system from miles away. To master the art of finding gold without a detector, your search begins not in the creek bed, but at the macro level, looking at how entire mountain ranges were stressed and fractured. Gold-bearing fluids require a highway to move from deep magmatic zones up into the upper crust. They find these highways along major tectonic fault lines, shear zones, and structural bends. When you stand at the base of a mountain range, you are looking for structural chaotic zones. Clean, smooth, uniform rock faces rarely hold rich hydrothermal gold. Instead, you want to look for zones where the rock looks shattered, twisted, and heavily contorted, where layers of mountain strata suddenly bend, break, or offset from one another. High-pressure fluids were once forced through under intense hydraulic stress. As these boiling, mineral-rich liquids blasted through the fractured rock, they triggered a massive geochemical reaction known as hydrothermal alteration. The fluids were packed with sulfur, silica, iron, and trace metals, and they were intensely hot and acidic. As this chemical soup washed through the host rock, it literally cooked the native minerals, transforming flexible, dark minerals into entirely new mineral compounds. This alteration zone is your primary target, and it paints the mountain in very specific, unnatural colors. The most widespread and easily recognizable chemical halo is Argillic and Phyllic alteration. When superheated acidic water attacks standard igneous or metamorphic rocks, it strips away potassium and feldspar, breaking the rock down into dense, pale clay minerals and fine-grained white mica known as sericite. From a distance, an alteration zone appears as a bright, chalky, bleached white or pale yellow band slicing directly across a dark mountain ridge. If you are hiking through a dark granite or basalt canyon and suddenly encounter a wide swath of rock that looks bleached, crumbly, and unnaturally pale, you are not looking at simple surface erosion. You are standing inside the ancient throat of a hydrothermal fluid channel. However, bleached rock alone is only half of the chemical equation. You must look for the oxidation of iron. Gold almost never travels alone. It is virtually always accompanied by massive quantities of iron sulfide minerals, primarily pyrite and arsenoparite. When these sulfide minerals are exposed to air and surface water over thousands of years, they break down through oxidation, releasing iron and sulfur. The sulfur turns into sulfuric acid, which further bleaches the surrounding stone, while the iron reacts with oxygen to form heavy iron oxides like hematite, limonite, and goethite. This process creates what geologists call an iron hat or Gossan. To the untrained observer, a Gossan just looks like a heavily rusted dark reddish-brown outcrop. But to a geochemical prospector, it is one of the most exciting sights in the mountains. A true gold-bearing Gossan has a distinct vesicular, honeycomb-like texture. As the sulfur and base metals leached out of the rock over thousands of years, they left behind tiny, hollow cavities inside a dense, dark red and orange iron frame. If you break open a piece of this rusted rock and see intricate, delicate voids lined with deep maroon hematite or bright mustard yellow limonite, you are holding the oxidized skeleton of a massive sulfide vein. The sulfur and base metals are gone, but the heavy chemical gold that was trapped inside those sulfides remains locked within that porous iron crust. As you move closer to the center of a hydrothermal system, the chemical signature shifts from soft clay and iron rust to intense silicification. Silica is the chemical backbone of quartz, and it is the ultimate transporter and capping agent for mountain gold. When silica-saturated fluids cool rapidly near the surface, they flood the host rock, replacing soft minerals with rock-hard microcrystalline quartz, jaspers, and chalcedony. This process turns soft, crumbly country rock into a dense, razor-sharp geological formation known as a jasperoid or silicified cap. Silicified zones are remarkably resistant to weather. While the softer rock around them erodes away, the hard, silica-flooded gold zone stands out as jagged, sharp crags, fins, and prominent spines sticking up along mountain ridges. When you inspect these silica caps, look closely at the quartz texture. Smooth, milk-white quartz with clean, smooth faces, often called bull quartz, is usually barren of gold because it formed slowly under cold, stable conditions. What you want to find is quartz that tells a story of extreme violence. Look for brecciated quartz, rock that was smashed into sharp fragments by hydraulic pressure, then cemented back together by darker gray, oily-looking silica or dark brown iron oxides. This gray, oily hue in quartz is often caused by microscopic particles of sulfide minerals and gold trapped within the silica lattice during rapid cooling events. Another crucial geochemical clue that requires zero electronics is the presence of Pathfinder minerals. Gold atoms are relatively rare in the Earth's crust, but the fluids that carry gold are consistently packed with specific, lighter elements that travel much further away from the main ore body. These elements form wide halo rings around the gold deposit, acting as mineral breadcrumbs that lead you straight to the core. The most reliable Pathfinder minerals in mountain environments are fluorite, barite, tourmaline, and manganese oxides. Fluorite is particularly revealing. It forms in vibrant purple, green, or yellow glassy crystals inside rock fractures. Purple fluorite forms when fluorine gas-rich hydrothermal fluids interact with calcium-rich rocks under precise temperature windows, the exact same temperature window where gold precipitates out of solution. If you find a vein of fractured quartz laced with deep purple fluorite and black tourmaline needles, you are standing inside a high-energy thermal conduit. Manganese oxide is another powerful visual guide. It coats rock fractures in delicate, black, tree-like patterns known as dendrites. While manganese dendrites are often mistaken for fossilized plants, they are actually mineral precipitates left behind by fluids that were rich in heavy metals. A rock zone featuring heavy manganese staining, purple fluorite, and iron-stained quartz is showing you a complete geochemical fingerprint of a gold-bearing system. Beyond the rocks themselves, nature provides a living geochemical map through plant life and botany, a science known as Biogeochemistry. Deep-rooted mountain trees and shrubs act as natural drill rigs, pulling water and dissolved elements from tens of feet below the surface. When plants absorb heavy concentrations of specific metals from underlying ore bodies, it affects their growth patterns, foliage color, and distribution across the landscape. In many western mountain ranges, specific trees like big sagebrush, juniper, and pine show clear signs of stress when growing directly over toxic, heavy metal-rich alteration zones, as their root systems draw up high concentrations of arsenic, antimony, and sulfur from underlying sulfide veins. The trees may exhibit stunted growth, yellowing leaves in early summer, or unusual structural twisting compared to the healthy forest surrounding them. Furthermore, certain indicator plants thrive exclusively in soils that are rich in specific minerals. For instance, some varieties of wild buckwheat and specific mosses have an exceptionally high tolerance for copper and iron, flourishing in the acidic, metal-rich soils of a Gossan, where other plant species cannot survive. When you see a distinct, clean line in the vegetation, where dense forest suddenly gives way to a patch of stunted, twisted trees growing in pale, rusted soil, you are looking at a botanical boundary, drawn by underground geochemistry. To pull all of these clues together into a successful search without a metal detector, you must use the strategy of hydrological tracing. Water and gravity are constantly breaking down mountain deposits, washing geochemical evidence down the slopes and into the drainage networks. Instead of wandering aimlessly across a mountain range, you start at the bottom of a river basin and work your way up using chemical elimination. You begin by examining the gravels at the mouth of a mountain stream. You are not just looking for heavy gold in your pan. You are analyzing the aggregate rock types in the creek bed. If the creek gravel consists entirely of clean, unaltered river cobbles, the drainage is likely cold and barren. But if you start finding pieces of cellular, rusted Gossan, bleached sericite schist, quartz laced with purple fluorite, or rock fragments painted in green copper oxides, you have confirmed that a hydrothermal system exists somewhere upstream. As you hike up the drainage, monitor every side tributary that feeds into the main creek. At each junction, examine the rock debris coming out of the side canyon. If the right-hand fork contains plain, clean granite, but the left-hand fork is loaded with iron-stained breccia and altered quartz, you eliminate the right fork entirely and follow the left. By continuously tracing these geochemical debris trails up the mountain, the clue envelope narrows. Eventually, the float rock in the creek will become sharper, larger, and less water-worn, indicating that you are nearing the source. When the iron-stained quartz debris suddenly disappears from the creek bed altogether, you know you have just passed the outcrop. You turn out of the creek bed, climb the canyon wall, and search the slope for the bleached, silicified iron-capped ledge where the material originated. Finding mountain gold without a metal detector is not about luck, nor is it about relying on luck or chance. It is about learning to recognize that the Earth leaves an unmistakable, large-scale signature whenever it creates a precious metal deposit. A metal detector can find a small nugget hiding in the dirt, but understanding geochemistry allows you to read an entire mountain range, identify massive, untouched ore systems, and pinpoint hard rock gold traps that no electronic device could ever detect. When you look past the surface and learn to read the colors, textures, fractures, and plants written into the landscape, the mountains cease to be just piles of random rock. They become an open book, pointing directly toward hidden wealth.